So up next, we have Casey Honniball talking about lunar hydration dependence on temperature from ground-based observations at 3 microns.
Okay, so hi everyone. My talk today is a perfect follow-on to Carl's, and it's going to talk about how hydration measured by the 3 micron band is dependent on temperature. So it's now been well established that hydration exists on the moon in the form of hydroxyl or water. It's most commonly studied through the 3 micron absorption band and has been measured by spacecraft and from ground-based telescopes. One important result from these remote sensing observations is that the hydration seems to be varying across the moon as a function of lunar time of day and latitude. The image on the left here is showing a map of hydration measured by the Moon Mineralogy Mapper on Chandrayaan-1 spacecraft. And on the right, we see estimates of abundance from hydration from the NASA Infrared Telescope Facility, or IRTF, located in Hawaii. Both of these observations are showing higher concentrations of hydration at higher latitudes. In the IRTF data, we can also see variations in hydration with the lunar time of day by looking at a constant latitude. This is harder to do with MCube, where the data was taken at only a handful of lunar times, while the IRTF is able to cover a wider range of lunar times of day ranging from 6 a.m. to 6 p.m. So with the IRTF, we are able to look at variations at the equator at times of day that are near the morning and evening, as well as noon. So by using wavelengths out to 4 microns, we are able, with the IRTF, we are able to strongly constrain thermal models. And what we found with the 3 micron hydration band is that it varies in a manner that is consistent with changes in abundance of hydration or hydrogen diffusing through the lunar surface, forming metastable hydroxyl. These observations with the IRTF provide confidence that the hydration or hydrogen is moving around the surface, migrating to colder temperatures at higher latitudes or towards the terminators. These plots are demonstrating the observed variations with the IRTF in 2 ways. The left is showing variations with latitude, while the right is showing variations with lunar time of day. Now, it sounds like the controlling factor for these variations of abundance might be the lunar time of day or latitude, but it's really temperature. So changes in hydration abundance with lunar time of day are created by the surface warming or cooling throughout the lunar day, and with latitude, the higher temperatures are at the equator and decrease with increasing latitude. So really the variations are due to changing temperatures. And so this top plot here is showing the higher hydration at high latitudes measured by MCube, and this correlates well with diviner temperatures shown on the bottom. So the goal of this project is to use the IRTF to understand the dependence of hydration on temperature. For this study, we are using chord profiles that extend from one pole to the next, like depicted by the red lines. We have collected 9 chords ranging from 6 a.m. to 6 p.m. with a temporal resolution of roughly 1.5 hours. We have looked at the morning chords and are beginning to process the afternoon ones. And for this presentation, I'm only going to show you one chord that was acquired at 9:30 a.m. lunar time. So these are going to be 2 videos that show normalized reflectance spectra with a line at 1. A 3 micron band can be seen when the data around the 3 microns is below the line. The first one here is showing a really nice deep 3 micron band. So now I'm going to start the video. So the red dot on the side of the plot here is going to show relative flux for each spectrum. When the temperatures are high, the red point will be high on the plot. The video on the right is showing the IRTF guider camera during the chord observation, showing where the data was actually acquired. So we started at the North Pole and are working our way south. And you'll notice that once the temperature increased, the 3 micron band is no longer present. But one important thing to note is that the 3 micron band didn't quite just disappear all of a sudden. It actually started strong and began to weaken as the temperatures increase and we move towards the equator. Once we start getting away from the equator and the temperatures start to decrease again, we'll see that the 3 micron band will begin to come back and will finally end on a nice strong 3 micron band. Now, if you're watching the guider images, you'll notice that the chord is actually covering all different types of terrains with shadows and sunlit areas. We have not yet begun to control for all of these differences and conditions, but plan to soon. And also we'll be taking into consideration the incidence angles that Carl was just talking about. So now if we plot the 3 micron band as a function of relative flux, we see that there are higher band depths at lower relative flux. Now, this is very preliminary work, and there are still a lot of things that need to be done with the data. First, we need to resolve the thermal model temperatures to align better with the diviner temperatures. We need to correct for negative values, which I believe are being created by the linear continuum that we use right now. Some negative values with a mean around 0 are expected due to scatter in the data, but the amount of negative values that we currently have and how negative they are needs to be addressed. And lastly, we need to fix the effects of saturation that are artificially masking 3 micron bands due to bad thermal model fitting. So like I said, this is all a work in progress, but we are beginning to look at this. But what we are seeing right now is a linear trend between hydration and temperature that are inversely proportional. This is actually different from what the hydration measurements in the UV see. So Hendricks et al. 2019 found a sharp decrease in the UV water ice band ratio at temperatures around 350 Kelvin, while we see a more steady decrease in hydration with increasing temperatures. The difference between the two could be due to the UV and the 3 micron band sensing different depths. The UV only senses the surface of grains, while the 3 micron senses the surface and interior. Also, the UV is 50 times more absorbing than the infrared. And so another possibility is that the UV hydration signal is so sensitive to the abundance and the abundance is so high that the signal might actually be saturated at temperatures until the temperatures reach 350 Kelvin. The 3 micron band, however, is less sensitive and so may not actually be saturated and therefore is revealing the variation with temperature at higher abundances and lower temperatures. So we are also looking at how water observed at the 6 micron band varies with latitude but a constant temperature. Using the SOFIA Airborne Telescope, we have collected observations at 4 locations along the terminator as depicted by these yellow points, plus 1 location at the north that is at a slightly higher temperature. The locations along the terminator should have roughly similar temperatures, and so we were looking to see if water is varying as a function of latitude independent of hydroxyl. We hope to have the data processed and in hand at the beginning of August, and hopefully many more observations with SOFIA to come to disentangle 6 micron water from the 3 micron hydration band. So that is all I had for today. Thank you.